Alright, hello and welcome back. My name is Cameron Kirk, and this is my series of videos on how to program and develop in Verilog. And in this video series, we are going to be using the Altera Intel DE10 Nano FPGA. In today's video, we are going to be seeing how to write Verilog code that implements a 8-bit adder with an exception, and I'll get to that in a second. So let's sort of talk about how we use binary to and logic gates to add numbers in the first place. And to explain that, I opened some block diagrams here. I'm going to get out of the way. So I just went on Google Images, or in this case Bing, and I went to Images, typed in half adder. So what we're seeing here is the block diagram for a half adder. And this is a way of taking two 1-bit values, so this is a bit and this is a bit, and adding them together. So 1 plus 1 should equal 0 with a carry. Let me see, well, yeah, so if I write this out, we're going to do 1 plus 1, and then it's 0, and then you move to the 2's place. Because remember, we're in binary, so we have to use a whole second digit to carry over. So that's what the carry out is. Any other time, it's going to be, the carry out is 0, so we can do it within 1 bit. So if we have 1 plus 0, it's 1. If we have 0 plus 1, it's 1. If we have 0 plus 0, it's 0. And keep in mind, there's no carry out here. And that is a half adder. So the reason why this is a half adder is because we are not incorporating, a carry in. So let's look at a full adder now. So here's a full adder, and this is a adder same as the half adder, but in this case we are allowing a carry in to be plugged in, and then we still have a carry out and a sum coming out of the full adder. So once again, we have a 1-bit value and a 1-bit value and a carry in 1-bit value. And this is just like what you did in school when you're learning to add decimal numbers, right? So if I have 8 plus 1, there's going to be no carry, so I can just add these numbers and stay in one column. And then if I have 9 plus 1, it's probably, oh yeah, it's fine. It's going to go back to 0, and we're going to have a carry. So there's a carry of 1, so we have to go into the tens place for the 1. And then in another example, if I have 19 plus, well, now let's, oh yeah, we'll do 19 plus 2. I mean, this is a really simple example, and it should be clear what's going on. 9 plus 2, we're going to go to 1 with a carry, and we add the carry, and we get 21. And then in this case, 99 plus 1, we're going to go to 0 with a carry, and then we're going to go to 0 with a 1. So I probably didn't need to get into all these examples, but in this case, we had a carry which made a carry. And as you can see, the input to do this column of adding is a full adder, because we're accepting input for a carry in, we're accepting an A, and we're accepting a B. And so when you look at this block diagram one more time, we're accepting input for a carry in, and then we have our first number and our second number, but we're limited to binary. So this is the logic gates required to give you a sum and to carry out logically. Okay, and you can see there's actually some extra work we have to do to factor in that carry in. The half adder was a lot simpler, and the half adder is actually what we do in the ones place in the very first column. And everything is still the same, but instead of counting up to 9 and then going back to 0, we're limited to just 0 and 1. So we can only have like 1, 1 plus 1. And then there's lots of videos out there that show you how to do addition in binary. So I'll just do this example I wrote out. So this is in decimal, this is a 3, so base 10. And then this is a 1 in base 10. So I'm adding 3 plus 1 should be 4 in base 10. And over here, this is the binary representation of what I just did on the right. So we're going to have 1 plus 1, which is 2, so that's a carry. And this is 0. And then I have 1 plus 1, which, or sorry, I have 2 plus 2, which is 4, so that's a carry. This is 0, and we have 4. And this is the binary representation of 4. Yeah. Cool. So enough of the paint. Let's actually get to the coding, because we're not going to make this a long video, but I hope that was enough of an introduction. One final thing before we actually get to the code. We saw the half adder, we saw the full adder, and this is just a 1-bit adder. So 1-bit adder, 1-bit adder, you can only add 1 bit to 1 bit. What if I have a 2-bit number that I want to add to another 2-bit number? So then you would make a 2-bit full adder. So what we have here is this is a half adder, and this is a half adder. Oh, sorry, no, the bottom here is a full adder. Let me make this image larger. Open image in new tab. There we go. Zoom in. Okay, so on the top here we have this half adder. So the least significant bit and the least significant bit are added together in a half adder. And the carry out is going to the carry in of this full adder below. So this is the same full adder we saw on the previous block diagram. And we're adding the next most significant bit with the other next most significant bit. And then we are given a 2-bit value as the output with a carry out. So I mean, technically you could think of this as a 3-bit output. But this is how you sort of chain. You start with a half adder, and then you start chaining on more and more full adders. So I could put an entire full adder below this and take A2 and B2 and add them together using C0. I plug that in as the carry in, and then I've just made a 3-bit adder. And you can just chain these together more and more and more, and you can see these logic gates. It's the exact same function of a 1-bit adder. You just chain them together using that full adder. Okay, so that is theory and operation for this video. I hope I didn't lose you along the way, but that's what we're going to be doing. So back to the catch that I wanted to mention as I open up a Quartus project. So what I'm about to show you is in fact an 8-bit adder. So you can imagine working with the block diagrams and in Quartus and dropping down all of these XOR gates and dropping down all of these AND gates to get an 8-bit adder. This thing is going to be massive. Like, you can see already how big it is to do a 2-bit adder. This thing gets very big very quickly, and it's just not practical to implement one of these using block diagrams. You're not going to sit there with the mouse and click and drag your wires. That's just way too much work. It is so much easier to do this in Verilog. So you can see how big this block diagram is for a 2-bit adder. Typically we work with 8-bit values, so we'd like to make an 8-bit adder. And making that, you're going to need 1 half adder, 7 full adders, all chained, daisy chained together to get your 8-bit adder. And that's a lot of clicking and dragging with the block diagram. So no, we're not doing that. I'm sorry. That's just nonsense. So we're going to be doing this in Verilog, and it is actually very, very easy to define this exact same circuit in Verilog. And it's actually just 3 lines of code inside of your project here. So let me get this defined really quickly before I continue talking. I want to go to my live demos folder. We're going to do vid9. This is going to be an 8. Do not start your project name with a numeral. It has to be alphanumerical characters to start. Otherwise, you're going to have some problems using the waveform. So I'm going to type out 8. Actually, I'm going to call it a byte adder. That's a great name for it. Byte_adder. Okay, click next. Click next. We're not starting with anything. Click next. Just in case if you want to program your board with this, we're going to click SE base. We're going to go all the way to the bottom. We're going to get the 6U23I7. We're going to click next, and finish. So in this video, we're not going to be actually programming the DE10 Nano board with this solution. And the reason for that is because what I'm about to show you, it implements a adder as we saw in this block diagram, and it's going to be an 8-bit adder. But what's missing are registers. We're not going to be implementing registers in this video. And registers are what you're going to use to actually store values in memory. You can literally think of it as computer memory. In Verilog, you can write code to just say, oh, create this register, and then it implements it. It literally implements it and synthesizes a register on the chip in the FPGA. So this isn't emulation. This is hardware actually just like, oh, magically there is a register here now. Verilog is capable of doing this, but we're not going to cover that in this video. And because we are not using registers in our design, we're not actually able to put it on the board and have it keep track of what number A, the value A is at, and what number the value B is at. So we would make register A, register B, make them 8 bits, and then our output or our results we would save into those registers, but we're not doing that in this design. Okay, enough jabbering. Let's actually see some code. So I'm going to go File, New. I'm going to get a Verilog HDL file, and I'm going to start defining my module. I'm going to call this byte adder. I'm going to use the same name as I had defined my project because this is my top level entity and it has to match. Let's do the port list in a minute. Not ready to do that yet. I'm going to say in module. Okay. So yeah. So okay. So let's do the port list. I just wanted to check my notes and make sure I am staying on track. So here's our port list. We have CBA, and we're going to have a let me pause the recording and switch to Visual Studio Code just to make the font size bigger. Actually, no, I'll leave this part in the video just in case you want to see how I code in Visual Studio Code. So I'm going to save this. And then I have here File Explorer. This is my directory where I just saved that Verilog. And I'm just going to right click it and open with code. It might take a moment to open up. I'm using Visual Studio Code just for the reason of I want to make the font size bigger, and there is not a way to do that in Quartus. And I just want to make sure that this video comes out clear and that everybody can see what we're doing very easily without having to get a magnifying glass out or look really closely at their screen. I'm actually just going to go one size bigger just because I can on the font size. Okay, so now you're really not going to miss anything that's happening on the screen. Okay, so we have our port list here, and I'm going to define my output for C, and I'm not done yet, but I'm just going to type that for now. And then for input, we're going to do A and B. Okay, but we want a byte adder or an 8-bit adder. So the new thing we're doing in this video is we're defining vectors. So I'm going to say C is an output, and I'm going to do the square brackets in front of C. And I'm going to say, when I say this out loud, I like to say 7 down to 0, including 0. So this is a output wire or output net that is a total of 8 wires, all defined under C. So then later on, if I ever needed to access a single one, I could say, okay, C0, and then I can assign that some logic or whatever I want to do. Keep in mind, this is not a register, so it is not capable of holding its value. It has to be driven. It has to have a driver. And usually a driver is an output of another module or an output of a logic gate. Those are your types of drivers, or ultimately drivers are coming from the inputs. So you do have to have, well, you can hard code a driver without it being an input. That is a possibility. But yeah, so just think of these wires dangling out of our module here, and they could be hooked up to anything you want. And these are net, so they're going to be driven. They have to be assigned a value, and they cannot remember that value or store that value long term. As soon as it loses the value or the value changes, it instantly appears in C, the output C. Same thing for A and B. I'm going to say 7 down to 0, so wires 7 down to 0 for A, and it actually applies the same thing to B. This is valid syntax. So we're saying everything that follows is an input, and it's going to be of size 7 down to 0, and that's for A and B. Okay, and one more line of code to define our 8-bit adder. This is going to be a continuous assignment, and we're going to say C is equal to A plus B. And we're done. That is all the code to write an 8-bit adder. So once again, I just want to draw attention to, imagine using the block diagram and clicking and dragging, and here, let's do this. Do you want to reload the file? Yes. Okay, so we just loaded in our changes. Imagine coming in here, saying new, getting the block diagram, and sitting here and trying to put, all right, let's get an XOR gate, XOR 2. Oops. XOR 2 does not exist, sorry. XOR. So we need an XOR, we need 2 more XORs. Imagine trying to sit here and do this for an 8-bit adder. That would probably take me easily 90 minutes. And I just did the same thing in, what, a minute? It took me a minute to write this whole module and explain what it all means as I'm going. Anyways, let's do a waveform and see how it works, and then we'll wrap this video up. No, we're not going to use a block diagram. So here is our code. Let's go ahead and run our analysis and synthesis. Make sure we're not missing anything or making any mistakes. This shouldn't take very long to do the analysis and synthesis, so just bear with me one moment. There it goes. And we're done. Great. Okay, so now that that has completed, we're going to go File, New. We're going to get our university program waveform in here. We're going to right-click on this blank area. We're going to go to Insert Node or Bus. We're going to go to Node Finder. We're going to list. We're going to do greater than sign. Look at how many things it listed out. We'll do the greater than sign to bring them all over. Click OK. Click OK. And look at that. So A is capable of holding 1, 2, 3, 4, 5, 6, 7, 8 bits. Same thing with B and same thing with C. If I click the drop down on A, you can see each and every single one of them. So A0, A1, A2, A3. This is exciting. So if I wanted to, I could do something special, but we're going to do the same thing we've been doing in every single video before this. We're going to apply a counter to A. So I select A, I click on this button up here that says C. I'm going to say, okay, increment every 100 nanoseconds, and click OK. And then let's leave B as 0 for now. So C should be matching what A shows in our functional simulation. And then if you really like to, if you right-click on your node, go to Radix, you can change what it's going to be displayed as. So I can have it display in hex, right-click, hex, right-click, hex, or you can have it display in decimal. Radix, right-click, unsigned decimal. Radix, unsigned decimal. So if you're not used to working with binary, you're not used to working with hex, you can switch into this mode. Okay, so let's see what our output is when we add A to B, which is always 0, and let's see what C gets. So I'm going to click on Run Functional Simulation, this button right here. I'm going to say yes to save. Save it, and we'll let that load. This should be really fast as well. There it goes. And look at that. So we have, can I zoom in? Oh, but not in the way I want to. That's fine. It should be visible. So when we have 0 plus 0, which is equal to 0, C is the result. We have 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, and so on. And it gets all the way up to, I guess it only goes up to 9. We should be able, with 8 bits, we should be able to get up to 255. No, not 255. Yeah, 255, right? Because FF. Well, how do we get this thing to run for a longer time? What is this? Snap to grid. All right, well, don't worry about it. There should be a way to extend how long this thing runs for. Only up to 1,000 nanoseconds, it looks like. Simulation settings. Whatever. It's not worth it. All right, so we're going to apply a counter to B. And let's have this guy increment every 200 nanoseconds. All right, and we'll click, what does this say? Run functional simulation. We'll save those changes. And there you go. So you can see 0 plus 0 is 0, 1 plus 0 is 1, 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 2 is 6, 5 plus 2 is 7. Things are looking pretty good. So that's pretty much everything I have for this video today. You can see the value of using the waveform again because we don't actually have the rest of our circuit defined. We've just defined this adder module, and we don't have the registers or anything for an accumulator or anything like that. So we can't actually put this on the board yet because there's just not enough there to fire it up on the board. But we can see how simple it is to write this in Verilog code. We can see how vectors work in Verilog, and we can also see how we can use the waveform to validate our design before we even have any sort of controls. Because like maybe a push button is going to increment what A is currently at, and then we feed the value of A from a register into this adder module, but we just don't have that defined yet. But the waveform is capable of letting us still see if our design is working properly. So yeah, we saw a vector definition for the first time, and we made a 8-bit adder, and it was not a lot of code. So hopefully you can start to see the power of Verilog, and I hope you're excited to join me in the next one. That's all I have for today. So thanks for tuning in, and I'll see you in the next one. All right, bye.